Last video before we get on to techniques of solving differential equations, which is going to be rad. It's going to be awesome. It's going to be a lot of fun. And we have a lot of techniques. So this last one is just showing when you're going to have solutions to a differential equation and when those solutions are going to be unique. So it's just a little subsection here. It's important, but after this we really don't go through and do a whole lot of it. So I want to just kind of explain it to you on where it's coming from. It is important. Sometimes classes just gloss right over this. So let's talk a little bit about when you're going to even have solutions, what those solutions mean, and when they're going to be unique. So let's talk more about differential equations. When we talk about solutions, we're almost always talking about solutions through a point. And if you remember back to our slope fields represented a general solution, and they were important. We like general solutions, but when we talk about specific solutions, we're talking about those solutions through a point. It took a specific initial value, a point, for us to determine what that one curve was that we wanted that went through that point, and they gave us a specific particular solution on that slope field. I hope you remember that. If you didn't watch the video, go back and watch slope field. So solutions to differential equations are most often considered at points. That gives us specific things we can work with. Otherwise, we're left with this broad idea, which does give us information about our scenario, but doesn't allow us to zone in on one specific case. So I talked about slope fields, how we needed that point for a particular solution. So there are going to be three cases for us to have solution, or well, three cases that can happen when we consider solutions to a differential equation at a point. Case number one, there's no solution. So case number one, if we have a differential equation and we're looking for a solution at a specific point, it might not exist. There's cases for that. Now, here's what that doesn't mean. That doesn't mean that differential equation has no solution. That's not true. If you look at the slope field, like we have been studying solutions to differential equation, there's a whole lot of solutions to that differential equation. It just depends on what point you want to pick for us to get a particular. So where a differential equation might have tons of solutions, there might not be a particular solution through one point. There's a difference there. So a differential equation can have lots and lots and lots of solutions, just none that go through a certain point. That's important. Number two, it could have infinitely many solutions through that point. So case one, got a differential equation, you got a point, there's just none that go through the point. No solutions go through the point. Or you could have a differential equation, got lots of solutions, you pick a point, and there's infinitely many that go through there. Sometimes it happens with equilibrium solutions. So tons or infinitely many solutions to that differential equation that happen to go through that point. That happens too. Case three is the one that we really want to grab a hold of and see when this happens. So case three, you have a differential equation, you have a particular, an initial condition, a point, and we find one unique solution to that differential equation in the neighborhood of that point. We're going to talk a lot. This first part of this video is a lot of me talking, explaining what the neighborhood means, why we need the neighborhood, what continuity has to do with it, why that means differentiability, since we're dealing with derivatives, what that has to do with being a unique solution in a neighborhood around that. So a little recap before we get into it. First thing, differential equations are these equations that have derivatives. We know that. We are going to consider solutions to be at points. That lets us go from a general to a particular solution. Remember slope fields, that's what we needed to get that particular. There's three cases. Case one, you could have a differential equation that just doesn't have a particular solution that goes through the point you are suggesting. That's case one. Even though other points have solutions, that's fine. That one point does not yield a particular solution. That's case one. Case two, you could have a differential equation where you consider a specific point and infinitely many go through there. It's not unique. Case three is what we really like to zone in on, where we have one unique solution to a differential equation at, let's just say, at a point. But really what it comes down to is in a neighborhood around that point. Here's why we need that. So we'll talk more about this as we get on to our our cases over here when we have existence and when we have uniqueness. But for a curve to be continuous, I'm just throwing this right now so that you understand where continuity comes about. For a curve to be continuous at a point, that's really hard to say that you have a curve continuous at a point if you don't consider a little bit before that point and a little bit after that point. That's called a neighborhood. So if you have a point on a graph, I say, is that point continuous? That doesn't make any sense because you need to know if there's points before that and points after that. So you know if there's a little bit of the function that leads up to that point and a little bit of the function after that point to say, at that point, we had some before, it was not an endpoint, and we had some after, it was not an endpoint. The big thing here is that continuity isn't really exaggerated, really emphasize that. Continuity is an open idea. That's important. That's what this says. For a curve to be continuous, we need a little bit ahead and a little bit behind that point for an open interval to exist, for us to get to it and leave it. That excludes this idea of endpoints. And that's what this is saying. It sounds really like funky, like a neighborhood, but for one unique solution, with the case of one unique solution to a differential equation, it's in a neighborhood of that point because that point itself must be contained in something that's continuous for us to have differentiability. Since we're talking about derivatives, we need differentiability, something to be differentiable, and for that to exist, we have to have continuity. You have to be able to get there and leave there for us to say there's one unique slope at that point. Do you remember that from Calculus 1? This is it right here. I'm going to get to it later. I'll refresh it when we get there, but at every point before that one, you can say, hey, there's one specific slope to this curve at that point. But as soon as you get here, an endpoint, you go, well, we can draw infinitely many slopes through that one point. If we consider the points before it like a one-side limit, yes, we can go ahead and say, yeah, well, it's this. But at that point itself, if you don't have anywhere you're going to, you can't talk about that being continuous. And for that reason, we can't give it this idea of being differentiable at that point without the preceding ones, like a one-side limit, and we need this continuity for our cases of existence and uniqueness to be there. So long story made real short, when we're looking at unique solutions, so one solution that happens to be unique, we're looking at continuity, we're looking at a neighborhood, we're saying you need to be able to get there and leave there for continuity to exist, and therefore for these two things to take place. So what are the things we're talking about? For a differential equation, let's say we got a derivative of y with respect to x that's equal to a function of x and y and an initial value. So we got a differential equation like we know and love. We have an initial value. Okay, that's a point. We consider solutions to be at points. Here's what's going to happen. If our function, so we just look at this, if that's continuous around the point that we are checking, so around our initial condition, you can't just say this function is continuous for everything. It might be continuous for all points, but specifically we're zoning in on solutions around a particular point, an initial condition. So if our function is continuous around that point, or more specifically, around the open interval of the x value that gives us that point, and that's what this says, specifically around the x value that's given us the point. So if we have a function that's continuous around that x value, so here's the big thing, the only thing you really need to remember is your x value for whatever that point is cannot be an endpoint for the interval that you're continuous on. It cannot be an endpoint. No endpoints are allowed. Continuity is an open idea. Continuity says you need a little bit ahead and a little bit behind whatever point you're checking. So whatever x value that gives you that point, you look at that x value and you say, is that at an endpoint of where my continuity starts or ends? If it is, you're not continuous there. If it is, that's failing this. Okay, that's not okay. So if our function is continuous around that point, an open interval, so A is not at an endpoint of continuity, then at least one solution exists on that open interval. That's cool. So we know that we have existence. Now, it didn't say anything about being unique. It said that if your function is continuous around the point, so open interval, a or whatever this value is not on an endpoint of continuity. That's the only thing you really need to remember here. Then you have at least one solution. If f of x, y, so if our function's not continuous for open interval, so either you have that point, so x equals a, might be like creating 0 on the denominator of a fraction, or negative inside of a square root, or at an endpoint of continuity. I'll show you some in just a minute. Then a solution is not guaranteed to the differential equation at that point. Remember that we can have a differential equation with lots of solutions at lots of other points, but at this point doesn't have one. That's what we're saying. So if your function is continuous around an open interval, so of that x equals a, so a isn't a 0 on a denominator. It's not a negative inside of a logarithm or 0 in a logarithm. It's not a negative inside of the square root. And it's not at the end point of an interval of continuity, then we can guarantee there's a solution. But if it's not, so if this function is not continuous for an open interval, then we cannot guarantee a solution to the differential equation at that point. Again, no endpoints. X equals a cannot be at the endpoint of an interval of continuity. That would be like this. This function's all the way continuous. You go, oh, this is really good. Oh, it's fantastic. It's all continuous. And then we get here. Oh, crap. Well, if that is the point that we are checking, and we're saying, does this differential equation have a solution through that point? We would need to be continuous in an open interval around the x value that gives us that. This, remember, open idea, get there, leave there. If that's not the case, then we cannot guarantee that a solution exists for that differential equation at that point. We fail to be continuous. We fail to be continuous on an open interval at that point. The endpoint fails us. Can't have an endpoint. So that guarantees that we have at least one solution. Now that means that we're in one of these two, right? We're in one of those two cases if we've satisfied that. The second thing would be uniqueness. Now, in order to do uniqueness for a differential equation or a solution to a differential equation through a point, you need to be able to take a partial derivative. If you're not familiar with that, I've explained that in Calculus 3. You can go, it's not hard, and I can explain it here when we're going through it. But basically, you just consider all the x's to be constants. So if you had x, y, and you took a derivative, it would not be a product rule. You would just take the derivative and treat x like 3 or something. So it's not hard, super easy. If this is also continuous around that point, so if the partial derivative of your function with respect to y is also continuous around that point, an open interval around the x value that gives that point, then the solution to that differential equation around that point, so in that neighborhood of that x value that gives that point, is unique. One more time all the way through. We're looking at them at points. There's 3 cases. We really want the last one to be the case that we're looking at. So here's what has to happen. The function has to be continuous around that point you're checking. It's got to be continuous in the neighborhood. X equals a cannot be a point of discontinuity, and it cannot be at an end point of an interval of continuity. That's it. It's all you really need, that statement. Listen to that a couple times. That guarantees that a solution exists, at least one. For the solution to be unique, you do the same check just with a partial derivative with respect to y. So you take the partial derivative with respect to y, just make sure that it's still continuous around that point. So x equals a does not create a discontinuity for you, and it's not at the end point of an interval of continuity. And if those two things are met, then you have one solution that's unique to that differential equation in the neighborhood of that point due to our continuity. That's it. It sounds a lot worse than it is. The main things are that you got differential equations at points. Check continuity. Check the continuity of the partial derivative. Just make sure that x equals a is not at an endpoint or isn't creating a discontinuity for you, and you're good to go. So we're going to go through several examples. They're all very, very quick. They're not hard things to do. I'll show you that, and then we'll move on. Let's get started with some examples, shall we? So again, all we're doing here, we're not solving. We don't have any techniques for that yet. What we're doing right now is just checking. to see whether a solution is even going to exist to the differential equation at that point that's given. So we're checking to see existence, and if there's existence, then we check to see if the solution that exists is unique or not. So let's try that. So a differential equation, dy dx equals 2x squared y squared, and we're checking to see whether that differential equation has a solution and whether that solution is unique at the point that's given by y of 1 equals negative 1. The first thing I always like to do, I like to write the point out. So x is 1 and y is negative 1. That's important. So x value and our y value. We'll talk about why that's important in just a bit. So the first thing we do, and it's not that hard, to check for just existence, what we're going to do is we're going to look at just the function. So the function of that we're looking at is this part on the right-hand side. So you solve your differential equation for dy over dx, and that right there is your function. We want to make sure that that function is continuous at the point that we are checking, or more specifically, around the x value that gives us the point that we're checking. Now, if you remember about discontinuities, you remember there's really only 3 places that we have got to worry about for discontinuities. They are denominators, so fractions that have variables on them where the denominator could equal 0. We don't have any fractions. Or square roots, fourth roots, sixth roots, even roots where we could have negatives inside. We don't have any radicals. Or logarithms where you have 0 or negatives. You're not having logarithms. In fact, that looks a lot like a polynomial, sort of a driven function, and so we know those are continuous everywhere. There's not a value of x or y that you can plug in there that's going to create a problem for you. So that function's continuous everywhere. Since it is continuous everywhere, it's got to be continuous around x equals 1. Remember, we're always checking around the x value. We're looking at that and saying, hey, is that continuous? We can check the y value too, but the idea is on the x. So we check our point and go, hey, is it continuous around that point? You could plug it in if you want. It works just fine. There's nothing wrong with this. There's no discontinuities anywhere. That's continuous everywhere. Specifically around our point that we're checking. So if that's continuous everywhere, and that everywhere includes our point, the neighborhood around that point, then we've proven that that differential equation is going to have at least one solution that goes through that point. I hope that makes sense to you. Now we're going to check to see whether that solution is unique. So we go further. So this is part 1. Part 1 said that's continuous around that point. Everywhere includes that point. Part 2 says, now take the partial derivative of that function with respect to y. If we do that, you need to get in the habit of partial derivatives pretty quick. It treats all x variables as constants. So you're not taking a derivative of that. There's no product rule here. Don't worry about that. All we're doing is saying, hey, just pretend that's a constant. Move that 2 in front, so we'd be multiplying to get 4x squared y. So just take the derivative of the y component here and mash it together with the product. And we do the same exact thing. Does that have square roots? Well, no. Does it have fractions? No. No variables on the denominator. Does it have logarithms? No. It's continuous everywhere. So with those 2 things combined, the first one says this function's continuous in the neighborhood of that point. That means that we have a solution that, at least we have one solution to that differential equation through that point. This says, furthermore, now that our partial derivative of f with respect to y is also continuous, this is continuous around this point, this is also continuous around this point, not only does a solution exist, that's 1, but the solution is unique, that's 2. So these 2 parts together say that that differential equation has one unique solution in the neighborhood of that point. one unique solution to that differential equation in the neighborhood of that point. Let's keep on going. So number 2, we now have differential equation equal, or dy dx equals x times ln y. The first thing that we're going to do, we're going to look at the point. Our point is 1, 1, so x equals 1, y equals 1. We're going to make sure that when we check continuity, we're continuous around that point. Even if other discontinuities exist, I don't care. I care that we're continuous in the neighborhood, an open interval around that point. So our function, I always write out the function. Our function is x ln y. And when we think about that, we think that, well, that's continuous everywhere for x. There's not a problem with our x's, but our y's have to be positive here. You can't have a logarithm with 0 or negative. So this is going to be continuous as long as our y's are positive. No zeros, no negatives. Look at our point. There's 2 things we check for. 2 things we check for. Number 1, is our x value okay? Yep, x's, there's no problem with x's at all. Is our y value okay? What I mean by that is it falling inside the open interval here? What that means is it couldn't have been an endpoint, so 0 would have been a problem. But is this y value in this interval of continuity? Yeah, sure. The open interval of 0 to infinity, 1 falls in there. So 2 things we check for. Does our x work? Yes. Does our y fall in the open interval of continuity? If this is continuous for y is greater than 0? Yeah, that falls in that open interval. That's awesome. That's what we want. So this statement right here says that we have at least one solution to this differential equation in the neighborhood of that point. Now we check the partial derivative. Partial derivatives leave x's alone, treat them as constant, and it takes a derivative of the function of y. Derivative of ln y is just 1 over y. So let's think about where this is continuous. This is continuous for any x. X is not a problem here. But y, we just need to know that y can't be 0. So this is continuous for y doesn't equal 0. So all this really comes down to is look at your function, look at where it's continuous, what problems you have, make sure your point is literally inside that, not at an endpoint, inside that interval of continuity. That guarantees existence. Now take a partial derivative, do the same exact thing. Look at where this is continuous. This is continuous for anything where we don't have 0. Y is not 0, so we fall in this interval of continuity as well. So this continuity says existence, this continuity says the existence is also unique. So there's one unique solution here as well. I hope you're picking that up. That's important. It's important to understand that when we're checking this, all we're checking is continuity. You just need to make sure that the point you're checking, which makes sense why we're checking points, you can't just say continuous everywhere all the time. This is not continuous everywhere. This is not continuous everywhere, which is why we look for specific points to say whether a differential equation has a solution or not. It's based on continuity around that point. So we look at continuity, we just make sure that our x values and our y values for those points don't cause any problems. They're not in the areas of discontinuity, and they're not at the endpoints for continuity. If there's one thing I can stress, no endpoints allowed. That's not okay. Let's look at the next 2. So you're going to get in the habit of doing this really quickly. You go along, go, okay, our function xy is a cube root of y. Cube roots of y are continuous everywhere. 0 is not a problem. Negatives are not a problem. Positives are not a problem. So that's continuous everywhere. The point we're checking is x equals 0, y equals 1. There's not even an x value. I can't even plug in x's. That's fine. Don't worry about it. If this is continuous everywhere, then we're clearly continuous in the neighborhood of that point. That's great. What this says is that this guarantees that we are going to have a solution. Well, that's a weird curly V. when we take the partial derivative, there's only y's up there, so we'd have y to the 1/3 power. If we do the derivative of that, we get 1/3 y to the 2/3 power. Well, that's continuous no zeros. That's continuous everywhere except where y equals 0. So now look at our point. X was 0. I don't care about the x's, not even x's up here. Is it continuous in the interval of y equals 1, or around y equals 1? Yes, 1 is not equal to 0. There's an open interval that surrounds 1 for which we're continuous. So we're not going all the way to 0. Like you could think, well, it's open for just past 0. Continuous from 0 to infinity. Absolutely. It's also continuous from -infinity to 0. The only place it's not continuous is when y equals 0. So if this falls in these open intervals, you're good to go. As long as we are not at an endpoint, that means that we're satisfying the second part of this. So this was continuous everywhere. That falls in everywhere. This is continuous for y doesn't equal 0. This is y doesn't equal 0. As long as our point falls in that interval, we are rock solid. So not only does a solution exist, it's also unique. So we have one unique solution. Now this is the same exact problem, obviously, but we have a different point. I want you to see how this works. So first part would be exactly the same. We still have the same exact function of x and y. It's a cube root of y. We still have a point over here, but it's a different point at 0, 0. This is still continuous everywhere, no matter whether we're 0 or not. It doesn't matter. This is continuous everywhere. What that does, that says that this differential equation has at least one solution through that point. You need to get that a solution does exist. Now we check uniqueness. Obviously the same thing, and obviously the same continuity. This function is only continuous on this open interval. It is not continuous at y equals 0, so that's an interval of discontinuity. So we already know that a solution exists, but when we check in the neighborhood of this point, well, let's check to see whether that solution is unique. You know there's at least one. Let's see if it's unique. We plug in 0, 0, or we look at the continuity, or we consider this interval around 0, 0, and go, well, no, that 0 would be an endpoint. We cannot be continuous at endpoints. Or another way to consider it is that 0 right there, that 0 for y, literally causes a discontinuity. If you have a value that's causing a discontinuity, you're obviously not continuous there. So this fails uniqueness. So we have, if it fails uniqueness, we have more than one solution. So we have at least one solution here, but it's not necessarily unique. We can't guarantee uniqueness. So we're checking, looking at the function, seeing whether we're continuous around that point. If we are, awesome, at least one solution. If we take the partial derivative and we're still continuous around that point, then that solution is unique. Let's try the next one. So where in the world is that continuous? Let's think about that. If there's one that you really should focus in on, it's this one, because this will throw you for a loop if you're not paying attention. So where are square roots okay? where are square roots continuous? Well, they're continuous as long as the inside is not negative. So as long as inside is 0 or more. Now I'm going to make a mistake here on purpose. I want you to watch very carefully. There's the mistake. That's a mistake right there. The inside's got to be positive. We know how to do domain, right? We know that square roots have to have a radicand, the inside part that's always positive. We know it's got to be greater than or equal to 0, but for continuity to happen, you can't have the equals part. Equals always means a bracket. It means closed. So don't be closed-minded, man. Just be open-minded, all right? So we can't have that. That's the board. So when we have this, we think, yeah, inside's got to be positive, but it's continuous on the open interval where x minus y has got to be strictly greater than 0. If we allow it to be equal, that's literally the endpoint. We cannot allow endpoints. Are you getting that? It's like 5,000, 6,000 times. We can't allow endpoints. Go a little further. That means x has to be greater than y. Add y to both sides. So we need a point where x is literally greater than y. Look at your point now. Our point is 2, 2. Is x greater than y? No. If we allow the equals to say, well, what about 0? That's fine. As soon as you do that, you now have an endpoint of continuity, and that is breaking the law for continuity. You cannot have that. So because this 2, because that is the endpoint of our continuity, that doesn't even go together. You can't have endpoints for continuity. So because that's where this function even starts to work, it's an endpoint. You cannot allow that. So when we say this is continuous for x minus y is greater than 0, we're disincluding that endpoint, then x would have to be greater than y. Does your point fit that? Does your point fit in your continuity? The answer is no. The x is equal to y. The x is not greater than y. Therefore, we cannot guarantee existence. If we can't guarantee existence, we certainly can't guarantee uniqueness. And you can see that if you really want to. So if we do the partial derivative, we're going to run into the same exact situation. So if we look at this, we have a 1/2 power. We got a chain rule going on here. So 1/2 inside to the negative 1/2 times the derivative of the inside. Well, the derivative of this with respect to y, that's a constant. That would go to 0 times negative 1. That's the same situation. We can't even allow zeros here at all. But this would say this is only continuous where x is greater than y. That would be the interval of continuity. Don't get it confused with the interval of where it exists, your domain. This would exist for the point, at the point 2, 2. The function would exist there at 2, 2, but not continuous there. Why would you check a point if it didn't even exist? I mean, that doesn't make sense. So obviously this point exists on this function. You would just get 0. You have an input of 2, 2. You have an output of 0. Fine. But when we check for continuity, we're not continuous on that entire interval. We're continuous on the open interval, not the closed interval. You must not include endpoints. So we can't guarantee existence. We also can't guarantee that that's unique. That makes sense because we don't even know if there is a solution. Now let's try the next one. So maybe you can try this. If you haven't already, give that a try. Pause the video. See if you can do that. Same exact thing. Same exact continuity. But now we look back at our point, we think that the point 2, 1, that's your x value, that's your y value. Does that point fit in continuity? So all of this stuff comes down to check the continuity, define the continuity. It must be open, no equal signs. Got to have open intervals here. You have to be open and then check to see if that point is on your open interval. If it is, you're good. Just make sure that it fits your continuity. So we know this is continuous for x is greater than y, not exists. Yes, it exists when x equals y, but continuous for the open interval of x just slightly bigger than y. If x is bigger than y, that's fitting our model for continuity, and that's guaranteeing that this particular differential equation has a solution, at least one solution, in the neighborhood of that point. Look at the comparison here. We mentioned it earlier, but this is the first time we really see it. We can have the same exact differential equation, one of which is guaranteed to have a solution at a point, and one of which is not at a different point. So that's why we always consider solutions to differential equations at points when we're talking about existence and when we're talking about uniqueness. So let's see if this is unique. Using the same thing here, well, if this is continuous around our point, then we know that our solution is unique. And when we look at it, we say, well, this is continuous where x is greater than y. Again, same exact thing. We can't even allow the equals for existence here. We literally need, because we have 0 in the denominator, that would be a problem. So we literally need x to be greater than y. X is greater than y, so we have one unique solution. I'm going to put 3 more on the board in just a moment, and I would suggest you try them on your own if you can. The idea is check the original, just make sure that whatever you've defined for your continuity, first that it's accurate, and second that your point fits it. Second, we do a partial derivative and do exactly the same thing. Don't include endpoints. If your point you're checking is at an endpoint of continuity, that is an oxymoron. You cannot have an endpoint for continuity. So let me go do those 3 other problems and then we'll call it good. So I'm giving you 3 more. After I show you what to do on the first thing, I would really recommend you try all 3 on your own if you can. There's one thing, these look a little weird to you. If they do look weird, remember that when we're checking our continuity, you have to have it of the form dy over dx equals some function x and y. So these 2 don't fit. So when you get something like that, the first thing I'd like you to do, just divide both sides by y. Get rid of that y. So if that's multiplied, you'd have to have dy over dx equals x minus 1 divided by y. That's the function you should check. And then you'll be able a lot easier to see, oh yeah, it's kind of discontinuous at y equals 0 or whatever. Same thing would happen here. So I would highly recommend you pause the video, give these 3 a try, do the best you can to do 2 things. Find the function, like we've done, see where it's discontinuous and where it is continuous, and see if the point satisfies that. You must not have endpoints. This must not create an endpoint for your continuity. It can't do that. Then you take a partial derivative and do exactly the same thing. So I'm going to get going on it, but you should pause the video and try it if you can. So for us, we've already determined that that's the differential equation we are checking to see whether that has a solution at that particular point. So I always make sure I'm setting up the problem correctly, dy over dx equals some function x and y. I'm also always writing down my point. The point is 0, 1. So I'm going to check to see where this is continuous. This is continuous for any x value. X is not a problem here. Plug in anything, you're going to be fine. But the y is a problem. Y cannot be 0. If it helps you to see the open interval, actually write out the open interval. So we'd write out negative infinity to 0, and then again from 0 to infinity. As long as this y value, so x is good, any x's. So we could also write, I'm being a little lazy, we could write down continuous for any x. So x would be all real numbers. And continuous for y that doesn't equal 0. Here's your interval for that. So all we're checking is this somewhere in this open interval? It certainly is. So this guarantees that this differential equation has at least one solution around that point. Then we take the partial derivative of f with respect to y. Well, what that gives us is You can do it several different ways, but this would be like x minus 1 times y to the -1 power. If you want to take the derivative of that, this acts like a constant, like 3 or something. We'd have negative, let's call it 3, y to the -2. So that would give us negative x plus 1 over y squared. That's what that would give us. And now we check continuity for this as well. Well, nothing's really changed, has it? X can be all real numbers, so this is continuous for all x values. It's continuous for y as long as y is not 0. And you can do exactly the same interval. In either case, we see that, yeah, it's the same exact continuity. So this function is continuous around that point. This partial derivative is also continuous around that point. So this has guaranteed us uniqueness for, existence and uniqueness. So this is there will exist one unique solution to that differential equation around that point, because we check continuity for both the function and the partial derivative. Are you getting that? I hope you're getting this. The second one, let's look at how it changes. Same exact thing. We would solve for our dy over dx. We know that our partial derivative would be exactly the same as what we just had. And now we're checking our point, not 0, 1, but 1, 0. Well, when you check that, you see it automatically. This is continuous for y does not equal 0. If y equals 0, you got yourself a problem. That y is causing the discontinuity. You're done. So this does not guarantee us that the solution exists. Same thing happens here. This can't be continuous if y is 0. Our y is 0. It's saying it's not continuous. So we failed continuity in both the existence and the uniqueness. So we can't guarantee existence, and we certainly can't guarantee uniqueness. I hope that's making sense as well. Last one, fairly straightforward. We have our differential equation. We've got our point 0, 0. All that it takes us to do is check our function. Now, 1 plus y squared, you can't have 0 in the logarithm. You also can't have negatives. But 1 plus y squared can't ever equal 0, and it can't ever equal a negative. So this is continuous everywhere. Continuous everywhere includes the point that we're checking. Now the partial. Partial derivative, well, a logarithm says you do 1 over the inside times the derivative of the inside by the chain rule. The derivative of the inside is 2y. 1 goes to 0, y squared goes to 2y. So our partial derivative is that. Now, because our 1 plus y squared can't ever equal 0, we don't have any discontinuities here either. You can't ever add 1 plus a positive and get 0. Doesn't make sense. So this is continuous everywhere as well. And for that reason, it's continuous around that point, around the neighborhood of that point. So function itself, continuous around the point. Partial derivative, continuous around the point. Again, we get one unique solution. I hope that makes sense. I hope now that we've fleshed out the idea, it's not that big of a deal to you. We're really just checking continuity around the point that you're given. Take the partial derivative, do the same thing. If you have both, then you have existence and uniqueness. If you have existence, it doesn't guarantee uniqueness. You got to check the partial as well. Okay, that's about it. Now, next video, we start getting on into how to solve differential equations. Exciting.